solvent pedigrees. So here's question 26 from chapter 4. This is 4th edition, and we have different pedigrees. I've solved this with other people before, but I'm doing it here again. So when you look at a pedigree, you want to find out whether it's dominant, again, don't mind my spelling, or recessive. Okay, and then you want to find whether it's autosomal or sex-linked. Okay, so that's what I usually do. First, I figure out whether it's dominant or recessive, then I figure out whether it's autosomal or sex-linked. For dominant, there are two things you want to look at. Okay, both parents can have the disease, okay, but they can have kids. Some might have the disease, some might not have the disease. It doesn't matter. Okay, parents, kids. And then the other thing is, when a child has the disease, so the child has the disease, at least one parent has the disease. Anyways, you get the point. I'm just saying it out, I'm drawing it, I'm not writing it out, but you heard it. So when both parents have the disease, you can have a mix of the kids having or not having the disease. And then if the kid has the disease, at least one parent has the disease. Okay, those were on the slides. For recessive, if both parents have the disease, so mom and dad has the disease, all the kids will have it. Regardless, they will have it. Okay, and then the second thing is, I forgot what the second thing is. Oh yeah, so when a kid has the disease, kid has it, you can see that both parents don't have it. So they're normal, meaning they're heterozygous for the disease, and they were carriers, and that's why the kid ended up with the disease. So first you figure out whether it's dominant or recessive, and then you go for whether it's autosomal or sex-linked. So if it's autosomal, both male and females affected equally. So that's for autosomal. For sex-linked diseases, you can have it being X-linked or Y-linked. If it's Y-linked, only males will carry it and have it. Okay, so it's only the males, like the fathers, that will give it to their sons, and then those sons will give it to their sons, and so on. When it's X-linked, okay, the father will only give it to his daughter, and the mother can give it to either her daughter, making her daughter a carrier unless the father also has it, or her son. Okay, so in case you see that the father is giving it to the son and also giving it to the daughter at the same time, so it's like the father is the one who has it and he gives it to both either. Anyways, you know that it's autosomal unless it's sex-linked recessive, and we'll look at different examples. Anyways, so here's a pedigree. Here is our question, and each one will represent one of those four cases. Dominant autosomal or dominant sex-linked, recessive autosomal or recessive sex-linked. So for this first one, I can see that I have affected children, but their parents are not affected. So I can see that it's definitely recessive. Oops. So for this one, it's recessive. And look at whether it's autosomal or sex-linked later. Same thing for this one. The kids have it, the parents don't, so it's recessive. Both parents are heterozygote for the disease. And then here, for each affected kid, at least one kid has the disease. So it's dominant. Same thing with this one, it's dominant. Okay, so I figured out whether it's recessive or dominant. Then I'll look at the patterns. So for the first one, I can see that both males and females are affected equally. So this is autosomal. For the second one, I can see that the sons are the ones that have it, meaning the mother was a carrier because the father didn't have it. The mother, and since it's recessive, the mother is a carrier and she will give it to either her sons or daughters, but since the father doesn't have it, so the daughters, if she give it to the daughters, they will also be carriers, but because the sons only have one X, so it's X-linked. Okay, and then for this one, I can see that the father has it, right? And I said it's dominant, but then we said the father cannot give it to the sons unless it's Y, and daughters don't have Y, so definitely not X-linked, because if it's X-linked, he cannot give it to his sons, only his daughters. So it's definitely autosomal. Cool. And then here I can see that the father gives it only to the daughters, so it's definitely X-linked. So we managed to solve this very easy. Usually short pedigrees are not enough. Like when it's 1 to 2 generations, you would like to see it many more generations, but these were like straightforward and to the point. Okay, so we solved part A of the question. They wanted us to indicate what are the different pedigrees. Then they're saying for each pedigree, what would you advise the parents in terms of what are the chances the kid might have the condition? So for pedigree number 1, and the kids are represented by the hexagon. Since I know that both parents are heterozygous, right? So it's het times het. The possibility of the child having the disease is 1/4. So that's if you guys remember your ratios. And then same thing for this one. Even though it's X-linked, and we said the mother is the carrier, right? So here we need to figure out the possibility of whether this mother is a carrier or a normal individual that does not carry the disease. So since we definitely know that mother number 2 is a carrier, which is represented in the sons, and the father isn't, so let me draw this pedigree. I know it by ratios, but it would be simpler if I showed it to you, so I'll just put X negative for carrying the disease and normal X. That means that this person does not carry the disease. So anyway, so I will have a normal daughter carrier daughter, normal son, a son who has the disease, right? So the possibility of the daughter either being normal or a carrier is 1 to 1. Okay, so she could either be normal or she could be a carrier. The possibility that she might have a kid who has the disease is, in this case, if she's just like her mom and she's a carrier, she could have a son only that has the disease. So that's 1/4. Sorry. First of all, the only way she can give the disease to someone, technically her son, is if she's a carrier herself, and we just said it's 1 to 1. So the possibility of her being a carrier is 1/2. And then if she looks exactly like her mom and the father is normal, so she'll also have this Punnett square result, and the probability of her having a kid who has the disease or the trait is 1/4. So the answer is 1/2 times 1/4, and that's 1/8. Okay, and then let's look at this. So since we know it's a dominant trait, and obviously the father here does not have it, the mother here is a carrier for it and for the normal disease. So because she will get one from her mom, one normal trait from her mom, and one disease trait for her dad, which makes her het. So it's het times homo